Okay, let's pick up where we left off last time, talking about Fermi liquid theory. So I'm gonna use a couple of results that we derived at the end of last lecture. So let me just remind you what they were. First of all, we derived the energy of a quasi-particle at momentum p and spin sigma. That we can write as the energy without interacting with other quasi-particles. So this quantity here is Vf star times P minus Pf, where Vf star is Pf over M star, with M star being a phenomenological factor. And then we have the interaction P prime sigma prime F sigma sigma prime P comma P prime delta N. Oops, move myself out of the way. There, delta N of P prime sigma prime. So all the P's being vectors here, I guess. The point here being that the energy of a quasi-particle at momentum p is shifted by the presence of quasi-particles with momentum p prime. The important assumption of Landau Fermi liquid theory is that the presence of other quasi-particles can shift the energy of a quasi-particle, but it can't actually scatter it. Okay. So then we made a number of mathematical transformations. F of p and p prime became an f of theta between p and p prime, and then we took the harmonics of that to give me f of L. For example, f0 was 1 over 4 pi integral over directions on a sphere, directions omega hat of f of omega hat, and so forth. And then we also took the symmetric and anti-symmetric parts, f up plus or minus f up down, where symmetric and anti-symmetric refers to the behavior of the spin. We also used the effective density of states at the Fermi surface, which is the volume of the system, m star pf over h bar cubed pi squared. And with this parameter, we made these small f's into big F's. F symmetric or anti-symmetric with angular momentum L is d star EF FL, symmetric or anti-symmetric, where these are dimensionless quantities. And the entire Fermi liquid is defined by the parameters defined by I'm assuming you have rotational invariance, spin rotational invariance. It will be defined entirely by Kf, M star, and the F parameters, where the F parameters are deformations, are the energies of deformation of the Fermi surface, energy of deformation of Fermi surface, and now I need to of Fermi surface. And so, for example, here's your Fermi surface. If you deform it like this, this is the zeroth harmonic. I in the last lecture I said something that was incorrect. I corrected it in the notes. That this is what an F1, the first harmonic of the Fermi surface, looks like. What I actually drew was something like this. This is an F2 harmonic of the Fermi surface, F2, so forth. So correct that in your notes as well. Okay, so now we're going to use Landau Fermi liquid theory to try to calculate an example, to try to calculate the compressibility. That's dN d mu, compressibility. So we do this. So obviously compressibility is related to this F. It's going to end up being related to this F0, so the compression of the Fermi surface. And the way we're going to do this is we're going to, come back. We're going to start with a Fermi surface here with momentum Pf, like that. And then we're going to shift the Pf until I'm going to increase it by going to change it by dpf. So it now has a different amount of density. That's going to be a change in density, and we want to know how much the chemical potential changes. So the new chemical potential is going to be the energy of a QP quasi-particle on the new Fermi surface, which we can write as E twiddle at Pf plus dPf, which we can then write as E twiddle of Pf, E no twiddle. Now we're plugging in this formula we wrote up here, way up here. I'm going to use this formula. We'll have, this will be E Pf plus dPf. That is the energy of the particle, the Fermi surface, when you don't include the interaction with the other quasi-particles, and then we'll add the interaction with the other quasi-particles. Sigma prime, P prime, dn, P prime, sigma prime. And this delta n here, what is the delta n? Well, delta n is of P prime sigma prime is equal to 1 for Pf less than P prime less than Pf plus dPf. So we're filling up this intermediate region here between Pf and dPf. So the change in density is 1 if you are between Pf and Pf plus dPf, and is 0 otherwise. So we can write mu new as mu old. It's just translating we're just translating this equation into slightly different form, and it will be plus Vf star times dPf. So the Vf star is, of course, Pf over m star. So this part here would be what you would get if you did not include interactions with all the other quasi-particles. You're allowing a change in the effective mass, but you don't care about if you didn't care about the occupancy of the other quasi-particles. And now I'm going to add the term that includes the interaction with the occupancy of the other quasi-particles. So I'm going to write this sum here as the number of p states between Pf and Pf plus dPf, the total number of states there, and then we'll write this as we're going to average over the directions. So this will be a sum over our sigma prime, f sigma prime, omega hat. It's just another way of writing that sum. Here I'm going to count the total number of states, and here I'm going to average over all possible directions, and that's just reproducing this sum up here. Okay. So the number of states between Pf and dPf is going to be 1/2 d of Ef times Vf and dPf. So because d here is the density of states, and Vf dPf is the change in energy, and 1/2 because a number of p states, density of states counts both spins, and this just counts total number of p states, which is only half as many as the number of space states when you count the spins. And this quantity here can be written either with the d real density of states times the real Fermi velocity for bare electrons, or equivalently d star of Ef times Vf star times dPf. If you go back to the definition of density of states up here, the density of states has an m star upstairs. Vf is I guess it's it should have a Pf downstairs. VF is PF H bar KF divided by M star. So the product of these two terms is independent of M star. So we can have M star, and sorry, this is VF star. So VF star times D star, or VF times D without the star. So either way, we get the same number of states here, same total number of density states, whether we write them both without the star or both with the star, and multiply it times PF. So this is just counting the total number of P states between PF and PF plus DPF. And then this quantity here is, in fact, averaging over the entire Fermi surface. It's actually 2 times F0 symmetric. So it's symmetric because we're summing over both spins. It's F0 because we're integrating uniformly over the entire Fermi surface. And it's a factor of 2 is in the definition. 2, if we look at the factor of 2 here, where does that come from? Right here in the definition of symmetric. Where is he? There, definition of symmetric. Okay. All right. So all told, we can now differentiate with respect to PF and get d mu dPF is VF star times 1. The 1 comes from this leading term here, plus when we put all of these factors together, oops, this 1/2 here cancels this 2 here. There's a D star and a VF star, so the VF star comes here. The D star times F0 small becomes an F0 big symmetric. And that's it. That's the whole thing. Okay? So we put together the small f with the D star to get a big F. V star comes out, differentiate with respect to this, and the 1/2 cancels the 2. Okay, so we're almost there. So what we're actually interested in is d mu dn, not d mu dPF. So let's just remind ourselves how we switch between the two. First in the non-interacting case. So in the non-interacting case, d mu dPF is just going to be VF. And dn d mu, n d mu is dn dPF times dPF d mu, and that will give me density of states at the Fermi surface, dEF times VF. That's the first factor, and so dN dPF is this factor here. This is dN d energy, and in dPF, maybe we should say that. So number of dN dPF is density of states of the Fermi surface, and then the dPF d energy. Density of states of the Fermi surface is dN d energy dPF is VF. So that gives me this factor, and then the second factor is just 1 over VF, and that just gives me the density of states of the Fermi surface, which is what we expected. Maybe another way to say that is if we back up to, okay, it's no more obvious, so we'll stick with that. Now in the interacting case, we now have what we just derived, d mu dPF, dPF is, we derived VF star, 1 plus F naught, and then we'll have exactly the same calculation. dN d mu is going to be dN dPF, dPF d mu. This factor of dN dPF is going to be exactly the same as it was before. It's density of states times VF, because this doesn't care about interaction. It's just number versus K. So this thing is going to be density of states at EF times VF again. And this second factor dPF d mu is just this thing upside down. So this is 1 over VF star times 1 plus F naught symmetric. It should be F naught symmetric. Did we write that in up here? Yes, F naught symmetric. That's good. Now this dE density of states of the Fermi surface times VF can be written, as we said before, as d star EF times VF star. So the VF stars cancel, and we're left with the final result. dN d mu is effective mass at the Fermi, effective density of states of the Fermi surface divided by 1 plus F naught S. So this is an interesting result. The point is the following, that the compressibility dN d mu is renormalized by the change in the effective mass by m star. That changes d to d star, but also by F naught symmetric. Okay, so the renormalization in the compressibility comes from two terms. One is the change in the effective mass, and the other is this Fermi liquid parameter. Okay, example 2. Let's look at Pauli spin susceptibility. And for spin susceptibility, we're going to take a Fermi surface which has both up and down spins, and we'd like to split those. So here's the old Fermi surface, and we'd like to maybe I'll make this one dotted. Okay, so the old Fermi surface is here, and then we'd like to this is terrible drawing. I'm terrible at drawing. And the spin-ups, we want to make more spin-ups and fewer spin-downs. Okay, so this was the old Fermi surface in the middle, which is now dotted. So let's call this PF. This thing that's dotted was PF. Is still PF, and then you're going to take some of the down spins and flip them over to make them up spins instead. Now this is, if you recall from your solid state physics course, or maybe even from your stat mech course, the Pauli spin susceptibility for non-interacting electrons is 1/2 g mu b. G is the usual g factor of the electron. Mu naught, that's the permeability of free space, times d density of states of the Fermi surface, and this is for non-interacting. Now, for interacting fermions, we're basically doing exactly the same calculation we just did for compressing the Fermi surface. So we exactly like we did before. We compress the Fermi surface and we calculate the what the energy is for doing that, or the change in chemical potential for doing that. But in this case, so that's what we did when we calculated the compressibility. But in this case, we're doing an antisymmetric procedure where we're compressing the spin downs to make the Fermi surface smaller for the spin downs, but we're stretching the Fermi surface for the spin ups to make the Fermi surface bigger for the spin ups. So in this case, what we get is, for the interacting case, is sort of a small exercise, which is not too hard. Chi Pauli is of the form 1/2 g mu b squared mu naught, and then we have d star EF. There's a mass renormalization. So the density of states changes to the effective density of states due to the mass renormalization, and then we have downstairs 1 plus F naught A. The antisymmetric mode of the Fermi surface, because we're interested in the spin downs doing the opposite thing as the spin ups. Now, one thing to notice, that if F naught antisymmetric is less than -1, then the susceptibility is negative, and the susceptibility of being negative, it means you have an instability. Instability, and the instability is to ferromagnetism. Stability. To understand why that is, remember that the energy cost of changing the relative size of the two Fermi surfaces is chi times the magnetization squared. If chi goes negative, which would happen here if F naught is less than -1, then the energy cost of changing the relative size of the spin up and the spin down Fermi surface is a negative energy, so it spontaneously transfers electrons from spin down to spin up, and you get ferromagnetism. So an instability gives you ferromag in this case, ferromag if that happens. And so example 3, this is a homework assignment, so I'm not going to do it in detail, but I'll sort of show you a little bit of how it works. The claim is that m star over the bare mass of the electron is 1 plus F1 symmetric divided by 3. So why is this? Well, the thing I messed up in the last lecture. So here's the Fermi surface, and the F1 mode of the Fermi surface, the first harmonic mode, first angular momentum, is a mode that just translates the center of mass. It just shifts the Fermi surface, make that like this, supposed to be the same shape, just moves the center of mass of the Fermi surface from one point to another point. Let me see if I can do this better with a bit of assistance. Okay, so here's my Fermi surface, and then I'm going to copy it, copy, and just shift it. Copy, and then paste. Paste, okay. There. Ah, that's beautiful. Okay, so this is the F1 mode of the Fermi. You take the center of the first Fermi surface and just shift it like this, like that. That's the first Fourier mode of the Fermi surface. So we can calculate the energy of shifting the Fermi surface by relating it to the F1 mode, symmetric mode of Fermi surface. But also, this is just a boost of the entire system. But also this is a boost. And when you have a boost of the translation invariant system, the total energy for making this boost has to be the total number of particles 1/2 m v squared, where this mass is the bare mass of electrons, bare mass of the fermions. It doesn't care about interactions at all, because you're just shifting the entire center of mass of the entire system. Okay, so equating these two different descriptions of this boosted Fermi surface to each other gives you this relationship between m star and an F1 symmetric. Okay, to give you an idea of what these parameters are, let's consider the primary example for helium-3. Helium-3, and the parameters do depend a little bit on what pressure you're considering. So 1 atmosphere, 33.5 atmospheres, and these are at temperatures which are well below the Fermi energy, but not so low that the whole thing becomes superfluid, which does happen at low temperature, low enough temperature, but that's extremely low temperature. So in this column, I'll put m star over m. This column, I'll put, let's make a couple columns here, so forth. I'm going to try them vertical. Okay, so m star over m in this column, F1 symmetric in this column, F0 symmetric in this column, F0 antisymmetric in this column, F1 antisymmetric in this column, and so forth. Okay, so filling in this table, m star over m at 1 atmosphere is about 2.9. F1 symmetric is about 5.8, and this has to satisfy m star over m is 1 plus F1 symmetric over 3. F1 symmetric here is just below 6, so 6 divided by 3 is 2, plus 1 makes just under 3, so that works. F0 symmetric is 11.5, F0 antisymmetric is minus 0.71, and so forth. And it changes at 33 atmospheres. It's about 5.8 m star over m. That would be related to 14.4, not an independent number. It satisfies this relation. And we have I guess 87.1 here, and minus 0.75 here, and so forth. A couple things to notice about this is that the renormalizations are enormous. The amount of that these are dimensionless measures of how much this motion on the Fermi surface, this change of the Fermi surface, how much energy it costs you compared to a free Fermi gas, and the renormalization factor is close to 100 here for making a pure compression of both species. Also notice that and this is interaction correction. This is the fermions are interacting with each other very strongly, and that's why you get a huge energy for trying to compress them that you wouldn't get for just compressing a non-interacting Fermi gas. Also notice that for F naught antisymmetric, this number here is even at 1 atmosphere. It's fairly close. It's not too far, from -1, which would be the instability to ferromagnetism. So it's very close to being ferromagnetic. Now, you might ask the question, well, we sort of described two experiments, compression and polyspin, where you compress the spin ups and uncompress the spin downs. And each of one got its own coefficient. And you might ask, well, are these just fudge factors? That for each different experiment you come up with, you define a new fudge factor, which gives you the ratio of what you expected to get, divided by what you actually got. And okay, so you defined one for effective mass, you defined one for compression, you define one for spin susceptibility, and so forth and so on. You can keep doing this. And the answer is it's not just a fudge factor, because really, it's just the first few coefficients that really matter for any experiment that you can possibly do. It turns out to be very hard to come up with an experiment that measures anything but the first couple of these Fermi liquid coefficients. Almost everything is determined by just a few parameters, and there's a huge number of experiments that you can do, and they're all described by just this small set of parameters. So we've only described just a very few experiments, but there's lots and lots of more experiments you can do, and they all give you exactly the same numbers. So one can go on. The main thing one does with Fermi liquid theory is you go on to upgrade it in the sense that the Landau theory of phase transitions was upgraded to Landau-Ginzburg theory, which gives you something about local properties of a system instead of just global properties of the system. So we're going to extend the whole idea of Landau Fermi liquid theory by taking our Fermi occupancy and P sigma, and this is again the quasi-particle occupancy that we've been using the whole time, and extend it to a quasi-particle occupancy defined locally. So this is like a Landau order parameter to a Landau-Ginzburg order parameter, where everything is defined locally, if you do know about a theory of phase transitions. Now, you might object, because here we're doing something you're not allowed to usually do in quantum mechanics, and that is we're specifying both the position and the momentum of a particle. So we really we're not allowed to do that, strictly speaking, but we can make some sort of semi-classical approximation where we describe some sort of wave packet where P is close to being defined and R is close to being defined, and the uncertainties in these in P times the uncertainty in R gives you something on the order of h bar Planck's constant. But if we're not concerned with looking at the details too closely, it's okay to try to define R up to some uncertainty and try to define P up to some certainty. And then once we've done this, we have some sort of phase space, semi-classical phase space density for both P and R. So how many quasi-particles occupy a given momentum at a given position, And from that, what one does is one writes down a Boltzmann equation. So very similar to Boltzmann equations that you might have derived from in other courses. You always start with the phase space density, and you see how the phase space density evolves in time. Now, we're not going to derive this because it's some amount of work. It's not a huge amount of work, but it is some amount of work. It's a little bit off topic, but it's worth knowing a little bit about what the solutions to the Boltzmann equation give us, which are so interesting. The Boltzmann equation has solutions, which are oscillations in the shape of the Fermi sea. So usually when we think about Boltzmann equation, we might be thinking about some fluid, and you might have oscillations of local densities giving you a sound wave or something like that. But in this case, you can have an oscillation which does not change the density, or maybe changes the density only a little bit, but where the Fermi surface is changing shape as a function of time and position. And these modes are known as zero sound. They are not usual sound. I'm not sure where probably Landau came up with the name. It was predicted by Landau for the first time, and it was observed in helium-3 in the 1960s. And what's particularly interesting about this zero sound is you compare it to normal sound, is that normal sound actually vanishes in a Fermi liquid, at T equals 0, whereas zero sound does not. So even at zero temperature, you can perturb a Fermi liquid and have a zero sound. So you can sort of think of it as the Fermi surface as being some elastic object, and you hit it like a bell, and it oscillates. It changes its shape as a function of time. So the shape of the Fermi sea changes, it oblongates, and moves back and forth. Normal sound is a pressure wave, and it's related to the thermodynamics, the local thermodynamics of a system. So if you remember how you derived sound in your fluid dynamics course, you start with an equation of state for some material. You need to know its compressibility, and you assume local thermodynamic equilibrium, and when you compress the thing, it sort of pushes back due to there's a change in density. The change of density gives you a change in pressure, and you get some oscillation back and forth. However, in a Fermi liquid, you don't have local equilibrium at zero temperature, and this is because there's no scattering of quasiparticles, of QPs. The QPs, once you make excitations above the Fermi surface, because of this principle that quasiparticles close enough to the Fermi surface do not scatter, they do not relax, it means you don't get to a local thermodynamic equilibrium in once you start a quasiparticle moving above the Fermi surface, it doesn't relax down to some other quasiparticle, and you can't derive sound from it of the local thermodynamics, or the local equation of state. So normal sound goes away at low temperature, but you have zero sound instead, which is a kind of remarkable result. So great. So this is everything we need to know about helium-3. So that's helium-3 equals Fermi liquid. But the Fermi liquid we're probably more interested. I mean, this is great for doing experiments. It's great for understanding the properties of fermions. But the Fermi liquids that people day to day are more interested in are electrons in metals. So what about electrons in metals? So get rid of this. And now what about metals? Now, metals are more complicated because they have long-range Coulomb interaction, and that makes things quite a bit more difficult. But it was addressed by Landau and Silin in 1956 became known as Landau-Silin theory. And Landau-Silin theory is admittedly a crude approximation, but it works very well for understanding many of the properties of a metal. So it proceeds in sort of two motivated steps. So the first step is to imagine a short range interacting Fermi system, short range interactions Fermi system. And if we're starting with our metal, we might say, well, let's include, for example, the Fock part of the interaction, Fock part, which is short range because the Fock interaction requires an overlap of wave functions. So the Fock part tends to be short range, whereas the Hartree part tends to be long range. So we can keep the Fock part, but not the Hartree part. So we're making some fictitious system that has only the short range part of the interaction, and we can calculate a response function, response of this fictitious system of this. So, for example, response of this, we might call it chi of q and omega. For example, we'll call it chi twiddle 0 at q and omega. So the twiddle and the 0 is meant to mean it's short range interaction, and so at for example, if I'm interested in the compressibility, that's chi twiddle of 0 at q equals 0 and omega equals 0. That's just dn d mu for this fictitious system, and that's d star over 1 plus f naught s, as we've discussed before. And the second step is to treat the long range part of the interaction, long range int, in self-consistent Hartree. Self-consistent Hartree. And the rules of self-consistent Hartree are very simple. It's you consider the response of a system to the externally applied potential, as well as any density that builds up due to the rearrangement of electrons within the system. So that's the rule of self-consistent Hartree. It's also the rule of RPA. RPA. The only thing that you do in RPA is instead of so the response, the total response function chi of q and omega is then chi naught twiddle of q and omega divided by 1 minus v twiddle chi naught twiddle of q and omega, and v twiddle is q. This is exactly like the RPA equation. The only difference is in the RPA equation you use the response of non-interacting electrons here for chi twiddle. We just use chi naught. Here we use chi twiddle naught. Chi twiddle naught includes the short range part of the interaction in its response. And here, whereas in an RPA, you don't, there is no short part of the range part of the interaction. Chi naught is really just non-interacting electrons altogether. And here I've upgraded it such that the chi naught twiddle includes short range part of the interaction as well that we calculate in Fermi liquid theory. So the chi naught twiddle includes the Fermi liquid corrections, and then this formula here, this RPA-like self-consistent Hartree formula, includes the Fermi liquid corrections. If we calculate this at q equals 0 and omega equals 0, and calculate how this thing screens, we'll find that the Thomas Fermi screening length squared is, well, what we had before, we had E squared density of states at EF. This is what we calculated for bare electrons. Now we get D star because there is mass renormalization, and we get 1 over 1 plus F naught symmetric from the compressibility renormalization. So this is a rather effective way to get the renormalization of of compressibility, normalization of the response from both the short-range part of the interaction and the long-range part of the interaction. It's not, it's not a systematic calculation except in certain limits, but it actually works pretty well, and it gives you a fairly accurate picture of how Fermi liquids with long-range interactions respond to perturbations. Okay, that's the end of this lecture on Fermi liquid theory. It is the end of the examinable part of this course, but next time we will start with the BCS theory of superconductivity, and I hope you will tune in. Whether you tune in before the end of the year or after the end of the year is up to you. There is a homework assignment on BCS theory, I think, so if you it's optional, I believe. But if you want to work through that, you might want to watch these lectures before the end of the year. And anyway, I will see you in the next lecture.